through our notes on the energy of matter and thermochemistry. So matter undergoes chemical reactions or physical changes. There is almost always going to be a change in energy. So we have been learning about the different types of chemical and physical changes and how we can identify those. In this part of our unit, we're going to be learning how to calculate, how to determine the quantity of energy that is being transferred when matter undergoes a chemical change or a physical change. The area of chemistry that studies this transfer of energy is called thermochemistry. So it's the study of transfers of energy as heat. That's where the thermo comes from, during a chemical or physical change. So we'll do a little review here from middle school on our two types of energy, which are potential energy and kinetic energy. We can abbreviate potential energy as PE and kinetic energy as KE. So potential energy is stored energy, or sometimes what we like to think of it as the energy of position. Versus kinetic energy is the energy of motion. So in terms of particles in chemistry, potential energy is that stored energy due to position. So when those particles are really close together, or there is a chemical bond that is stored energy, and then as those particles start moving faster and those attractions become less and they start moving faster and spreading out, that's a decrease in potential energy and an increase in kinetic energy. So the way we measure the average kinetic energy of these particles is by their temperature, obviously using a thermometer. Temperature is nothing more than a measure of the average kinetic energy of particles. Okay? And notice it says it's the average kinetic energy. So it doesn't matter how many particles you have. So you could have a 60-degree water in a teacup, and that would have the same temperature or average kinetic energy as the particles in a 60-degree bathtub of water. So temperature is different than heat, which we'll talk about here in a few minutes. So the two units we use for temperature could be Kelvin or the degrees Celsius. And you'll see here in your unit packet the conversion, the kind of formula we use to convert between Kelvin and Celsius. So if you want to go ahead and take a moment and pause the video to go ahead and write down that conversion factor between Kelvin and Celsius. The nice thing about the Kelvin scale is that it starts at 0, what we call absolute 0, and it just goes up from there. There are no negatives in the Kelvin scale. Versus in the Celsius, it does have it does go into the negative. So you're going to find throughout this year that there are going to be some formulas we use where the temperature must be in Kelvin because it does not have a negative side to it. All right, so there's a few practice problems here, just using this conversion between Kelvin and Celsius. So we have our first one, and then we'll do this one as number 2, and then we'll do this one as number 3. Sorry, the numbering got a little bit off. All right, so the first thing we're going to do is convert 25 degrees Celsius to Kelvin. So Kelvin is 273 plus the temperature in Celsius, 25 degrees Celsius. So we'll just add those together, and our Kelvin temperature is going to be 298, and you'll just write a K. There's no degree sign on that. Notice that for my precision, since it's adding, I go by place value. This 273 is a conversion factor, so do not use this for sig figs or precision. This is actually 273.15, and there's numbers that come after it. But my measured number here goes to the ones place, so my answer for my temperature should also go to the ones place. Right, let's try converting negative 15 degrees Celsius to Kelvin. So this will be number 2. So your Kelvin temperature is going to be 273 plus negative 15 degrees Celsius. If you can use your calculator or do this in your head, you get 258 Kelvin. Okay. Number 3, we're converting 0 Kelvin to Celsius. So the 0 Kelvin in here is equal to 273 plus the temperature degrees Celsius. So subtracting 273, we get a temperature of negative 273 degrees Celsius. That is absolute zero. That is the lowest possible temperature. That is when all molecular motion would stop. Okay? So temperature is just a measure of the average kinetic energy. The units we'll be using will either be Kelvin or Celsius. We should be able to convert back and forth between these two. The formula should be under Unit 2 in your unit packet. Okay? Heat is different than temperature. Heat is, we always make a comparison for heat. So the amount of heat is going to be determined by the temperature of the substance and the number of particles, the mass of it. So if you had a teacup of 60-degree water and a bathtub again of 60-degree water, the bathtub is going to have more heat because there are more particles moving at the same average kinetic energy. So heat is different than temperature. Heat always transfers from the higher to the lower temperature. Okay? So it always goes from high to low, so from the hotter to the cooler, because cool really is just the absence of heat. These transfers we can describe as being either endo or exothermic. The prefix endo means in, the prefix exo means out. So for an endothermic process, heat is absorbed into the object, making the surroundings feel cooler. Okay. So if you imagine holding an ice cube in your hand is feeling cooler because the ice is absorbing the heat from your hand. Okay. So that's an endothermic process for the ice as it absorbs heat from your hand, causing the particles to speed up, making them change from a solid to a liquid. That is making your hand feel cooler because the ice is absorbing heat from it. Exothermic processes, heat is released, making the surroundings feel warmer. When we do calculations with heat, you'll find that if you get a heat calculation that is is positive, that is going to be an endothermic process versus an exothermic process that's going to end up being a negative heat number. All right, so the units we use for heat could be either the joule or the calorie. Okay, so the joule is the SI unit that's used to measure the amount of energy, which in this case this is the amount of heat that is being transferred. Okay, the joule, you can have kilojoules, millijoules. You can use those metric prefixes in the front of it. The other unit that's used for heat energy is the calorie. We see this a lot in food science. The calorie is how we measure the amount of energy in our food items. It is just another unit used for heat energy. Now, this is a little c calorie. That is different than the big C calorie that we see on the back of our food labels. So, one big C calorie is equal to 1,000 little c calories. Okay? So really, if you had, 120 calories on a food item here in America, that really is 120,000 calories. So that's additionally the big C calorie on your food labels versus the little c calorie that we would have here. So that's also, since it's 1,000 little c calories, that would be equal to 1 kilocalorie. Okay? So that kilocalorie is 1,000 little c calories, the same as any other metric unit that we've been using. All right, so the other part of this that we will need to do our calculations is something called specific heat. This is a physical constant. Okay. So that means that it is unique to every substance. Every piece of matter would have its own specific heat constant that you would look these up. So these are values that you would have to look up in a table. Maybe use Google, find a reliable resource to find a table that has specific heats for you. Okay? So I call this a lookup value. So specific heat, the definition of it is the amount of energy needed to raise the temperature of 1 gram of a substance by 1 degree Celsius or 1 Kelvin. So the units are kind of funny. You'll see some examples here on the bottom left of your page. It's going to be joules per gram degree Celsius, calories per gram degree Celsius, or the temperature could be in Kelvin. You may see kilojoules in there at some point. Really pay attention to what units are being used and wherever you're looking at the value. In your unit packet here on page 8, there is a table that I've given you to be able to use in any lab or homework that you're given. So these are specific heats of common materials. You'll notice that water has a specific heat of 4.18 joules per gram degree Celsius. What this tells me is that it takes 4.18 joules of heat energy to raise 1 gram of water by 1 degree Celsius. Okay? That is very different than the amount of energy that's needed to raise the temperature of 1 gram of lead by 1 degree Celsius. Okay, so just stop and think for a second, which one would require more energy to raise its temperature? So we're going to be looking for the material that has the highest specific heat. So water is actually going to require more energy per gram to raise it by 1 degree Celsius. So water is going to heat up more slowly than lead would. Lead would heat up very quickly by applying the same amount of heat to it. Okay? So it would go very, very quick. It would increase in temperature very quickly compared to water. That's actually why water allows for life on Earth, because it takes so much energy to raise its temperature, which means that we moderate the temperature on Earth a lot easier than, say, if our atmosphere was made out of methane that has a much lower specific heat. Okay, let's take a look at the next page, because this is solving thermochemistry problems. We have two formulas. I want you to pause the video for a second and go ahead and write these two formulas on your purple sheet. That is Q is equal to MC delta T, and then delta T is the T sub F minus T sub I. Okay. Delta, anytime you see a delta in a science formula, that means change it. Okay. So we're looking for the change in the temperature, and for this it has to be final minus initial. Okay. So we have our two formulas written on a purple sheet. So Q is our symbol for heat energy. Units are going to be joules or calories. M stands for mass in grams. C is a specific heat. Remember, this is a lookup value. And then delta T is always final temperature minus initial temperature. And it has to be in that order. So let's use this formula to do a few sample problems. Okay, how many joules are absorbed by 100 grams of water if the temperature is increased from 35.0 degrees Celsius to 50.0 degrees Celsius? So we are going to, let's go ahead and lay out our Q is equal to MC delta T. So these are our variables. Let's see what information we have given to us. Q is going to be measured in joules because that's heat energy. So that is our unknown in joules. M is mass, 100 grams. C is specific heat. Now, for this, specific heat is a lookup value. So you want to flip back in the packet, go down to the table here, and you'll see that water has a specific heat of 4.18 joules per gram degree Celsius. And so we're going to need that for specific heat. That unit is joules per gram Celsius. Delta T is always final minus initial, so that's 50 degrees Celsius minus the initial of 35. And you can go ahead and solve that, so it's ready to go for your formula. That would be 15.0 degrees Celsius change, and that's a positive change because it's final minus initial. The final is higher than the initial. So we're plug this in. Q is equal to the mass times the specific heat, 4.18 joules per gram degrees Celsius, times the change in temperature, 15 degrees Celsius. Now you can look at the units and see if you have this set up correctly. So I can see immediately that grams cancel, temperature cancels, the Celsius units were left in joules, and that is what we're looking for. So go ahead and multiply these together. And calculate your answer is 6,270 joules. And that actually is the right number of sig base because this one has 4. Don't look at this one because that's a lookup value. This one has 3, so your answer has 3. So we are done on that one. The final answer right here. Okay, let's try number 2. This time we're looking for the specific heat of water. So a beaker contains 250 grams of water. It's heated with, 250 grams of water heated with 1,500 joules of energy. If the temperature of the water changed from 22 to 23.44, what is the specific heat of water? So usually the specific heat is a lookup value, but this time we're using lab data to go ahead and solve for that. So we're going to lay this out. So Q is in joules, 1,500. M is mass, 250 grams. C, we don't know. Delta T, final minus initial, 23.44 minus 22, 1.44 degrees Celsius increase. Let's go and put this into the formula. So 1,500 joules equal to mass. So we're going to take 1,500 divided by 250 grams times 1.44 degrees Celsius. And with 3 significant figures, we get 4.17, and then check your units. Joules per gram degrees Celsius. And yes, specific heat does have some funny units to it, and that would be the let's look at number 3 because there are 2 parts to this one. We have 1,800 joules of heat energy is applied to a 120 gram piece of aluminum whose specific heat is 1.89 joules per gram degree Celsius. We want to know what the change in temperature of the aluminum is. So we have Q is 1,800 and mass is 120 grams. C for aluminum, 1.89 joules per gram degree Celsius. Delta T, we do not know. So we're going to solve for delta T, okay? The change in temperature. So 1,800 So we're solving for that change in temperature. Let's take 1,800 divided by 120 times 1.89. And we get a change in temperature with 2 significant figures because of the mass having 2 significants here of 7.9 degrees Celsius. So the temperature had to increase by 7.9 degrees. Okay, so our part B here is if the aluminum had an initial temperature of 25, what is the final temperature of the aluminum? Well, we know delta T is equal to the final temperature minus the initial temperature. From the previous problem, delta T is 7.9 degrees Celsius. We know that the initial temperature is 25 degrees Celsius. We want to know what the final is. So we take 7.9 degrees Celsius is equal to the final temperature minus the initial. So we're just adding 7.9 and 25 degrees. So a final temperature of 32.9 degrees Celsius. Okay. Let's take a look at the problems that we've done and see if we can figure out if they were endothermic or exothermic. So in number 1, it says that the joules of energy are absorbed. That means that it is endothermic. This energy is going in. And the other way we know is because Q is a positive number. In number 2, it says that it's being heated with 1,500 joules of energy, and the temperature went up. This is a positive Q, so again, we have another endothermic. And then number 3, 1,800 joules of energy is applied. That's a positive Q, so again, endothermic, and that makes sense because the final temperature is higher than the initial. Okay, I'm going to leave number 4 for you to try on your own. I will give you the final answer for this. It's going to be 24.4 degrees Celsius. So I would like for you to try this one on your own and see if you can get to that correct answer. There's a kind of an algebraic way of solving this, and then you can also solve it like you did in example problem number 3. So I'll be interested to see what problem solving methods you guys come up with to solve for number 4. Be careful because it does say energy is released. So think about what does Q have to be and when energy is being released instead of being absorbed.